In this video, we shall be discussing quantum numbers. Quantum numbers are a set of values that describe the characteristics of electrons in an atom. They are used to describe the arrangement of electrons in atoms and the energy levels they occupy. There are 4 quantum numbers. Together, these 4 quantum numbers define the unique quantum state of each electron in an atom. Pauli Exclusion principle states that no two electrons in an atom can have the same set of quantum numbers, and which helps us explain the organization of electrons in atoms orbital.
Quantum numbers. These quantum numbers gives us the exact location of an electron in an atom. So we'll be going over this quantum number one after the other. So we have the principal quantum number, which has a symbol of N. Principal quantum number says principal quantum number. Just put like this, principal quantum number. Now we have the azimuthal quantum number. By the way, the principal quantum number is associated with the energy levels of atom. Energy levels within an atom, So let's take, for instance, if we have hydrogen, I will have the first energy level, second energy level, please forgive my drawing, the third energy level. Now for the first energy level, N, which is a symbol of principal quantum number, N is equals to 1. The second energy level, N is equals to 2. The third energy level, N is equals to 3. So these are the 3 energy levels. Now, next we have the azimuthal quantum number, or the angular momentum quantum number, and it's represented with the symbol L. And for this, let's say the azimuthal or angular quantum number. This is G, please. Angular quantum number. Right? We have the azimuthal, this is THO, please. We have the azimuthal or angular quantum number. Now, azimuthal angular quantum number is associated with sub-levels. It's associated with sub-levels. Now, we have ML. And ML is referred to as magnetic quantum number. Magnetic quantum number. Magnetic quantum number. Now for ML, magnetic quantum number has to do with the specific orbitals within a sublevel. Now, the last one, we have the MS, which is a spin quantum number, right? The electron spin. Now, we know that electrons either spin up or spin down, right? So, if it is spin up, you know it's plus half, and when it is spin down, it's minus half. All right. So let's look at the relationship between principal quantum number N and azimuthal quantum number L. So first and foremost, I want you to be familiar with this relationship. It states that when L is less than or equals to N minus 1. Now, what this means is that if N is 0, let's say N is equals to 1. Sorry, N cannot be 0. If N is equals to 1, L is equals to 1 minus 1, because L is equal to N minus 1. 1 minus 1 is 0, so L is equal to 0. So if N is equals to, let's say 2. L, going by that relationship, L is equals to n minus 1, so L is equals to 1. So that is how you are able to define the relationship between principal quantum number and angular momentum or azimuthal quantum number. The number of sub-level is equals to the energy level. So let's say, for instance, we have n, which is the number of sub-level, it's equals to 3. And we know that going by this our relationship, L is equals to 2, right? Now, when L is equals to 0, it is S. When L is equals to 1, it is D. It is P, sorry, P, not D, P. When L is equals to 2, it is D, right? Now, since n is equals to 3 and L is equals to 2, when you are representing this particular relationship, you are going to say 3s, 3p, that is when you are doing your electronic configuration, 3p and 3d. You know what that means? It means that this is 0, 1, and 2. So you see, at the end of the day, the number of sub-level, is equal to the number of energy level, right? So now let's look at the relationship between azimuthal quantum number L and magnetic quantum number ML. Right? So now that we are trying to find out the relationship between principal angular quantum number and magnetic quantum number, there's also a relationship that defines this relationship, and that states that minus L is less than or equals to ML, and ML is less than or equals to plus L. So this is a relationship. It says that minus L is less than or equals to ML, and ML is less than or equals to plus L. So what this basically means is that when L is equals to 0, ML is equals to 0, right? Because minus 0 is still 0, plus 0 is still 0, right? Then when L is equals to 1, ML is equals to minus 1, 0 plus 1. When L is equals to 2, ML is equals to minus 2, minus 1, 0, minus 1, plus 1, plus 2. Right? So, when L is equals to 3, ML is equals to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So this is the relationship between ML and L. Let's say, so if L, like we've said about the relationship, if L is equals to 1, right? And you know 1 signifies, it stands at P, like we said earlier. So you know, as we described earlier, we said ML, which is our magnetic quantum number, is associated with the sub-levels with. So you know, we say ML is associated with the sub-levels within an atom, right? Now, given the relationship we just discussed, the relationship between ML and L, now we know that ML, it gives us the description of which orbital the electron is in. So let's say, using the relationship we just discussed, let's say L is 1, ML, you know ML is going to be ml is going to be minus 1, 0, plus 1, right? Now we have the orbital diagram. An orbital diagram is going to be like this. You know, 1 first of all is p, and p has 3 degenerate orbitals, right? So we have 1, 2, 3. So therefore, we know that for ml, we have minus 1, we have 0, we have plus 1. If, for instance, L is equals to 2, ml is equals to minus 2, minus 1, 0, plus 1, minus 2. So this is our ml. Now, because this is our ml, we know that 2, first of all, we know 2 is what? Is a D. Now, D has 5 degenerates. So we'll draw the orbital diagram of D. Has 5 degenerates, 1, 2, 3, 4, 5, right? Now we know that this will be minus 2 for ml, minus 2, minus 1, 0, plus 1, plus 2, right? So then we'll now put the electrons inside to know the exact location, the exact orbital where the electron is in. You know, for the ms, electron spin, we know that in each orbital, the electron spin could be up or down. So it could be up or it could be down, right? And if, for instance, it's spin up, we know that it's equals to what? Plus half. If it spins down, we know it equals to what? Minus half, right? So let's take some examples so that we understand more clearly what we're talking about. So here is the first example. We have 3p2. Now we have an electron which is at 3p2. We have to find all the 4 quantum numbers of this particular electron. So before we go further, please friends, hit the like button. And if you like this video, please subscribe. So, to find the 4 quantum numbers of this particular electron, we start with the principal quantum number n. Now, the principal quantum number n, usually whenever you are given something like this, the last number behind here is always the principal quantum number. So in this case, our principal quantum number is equals to 3. Right? Then what about our azimuthal quantum number? L. Azimuthal quantum number L is equals to 1. Now, if you are confused, we discussed earlier that S is equals to 0, P is equals to 1, D is equals to 2, F is equals to 3, and so on and so forth, right? So now in this case, we have 3p2. So because it's P, L, which is our azimuthal or angular quantum number, is equals to 1. Now, to find the ml and ms, right? Now for ml, we will draw the orbital diagram. So we draw the orbital diagram, and by the way, p has 3 degenerates, so you draw the orbital diagram according to p. 1, 2, 3, right? Now ml, it's equals to, this is L is 1, so it's going to be minus 1, 0, plus 1, right? So we have 2 electrons because it's 3p2, 2 electrons, right? Remember Honsru said that you put singly before pairing, right? So you put the first electron, you put the second electron. So the second electron falls at 0. ml is 0. Therefore, ml is equals to 0. Now for ms, we know that when it spins up, it's plus half, and when it spins down, it's minus half. Therefore, ms is equals to what? Plus half. Right? So these are the 4 principal quantum number. What if you are given another equation? Let's say another electron, you have 4d9. Find all the 4 principal quantum number of this particular electron. So now we know that n is equals to 4. The number outside here. L is equals to 2. because it's D is equal to 2. Now for Ml, right, our magnetic quantum number, Ml is equals to, we'll draw the orbital diagram again. D has 5 degenerates, right? Therefore, we have 1, 2, 3, 4, and 5, right? Now, Ml, it's equals to D, L is 2, so it's going to be minus 2, minus 1, 0, plus 1, plus 2, right? Now, we have 9 electrons. Going by Hund's rule, we're going to put 1, 2, 3, 4, 5. Then we'll put 6, 7, 8, 9, right? So Ml falls at, so since the last electron falls at Ml falls at plus 1, Ml is equals to plus 1. Now what about our Ms? Now for Ms, remember that the last electron is pointing downward, so it's going to have a negative spin. So this is going to be minus half. So these are the 4 quantum numbers of this particular electron.